All right, good morning, everyone. Our first lecture today is by Professor Silviu Pufu from Princeton University, and going to tell us about gauge theories at strong coupling and ADS-CFT duality.
Okay. So there's a summary of the introduction to ADS-CFT that I went over last time. So just to remind you, in one of the best studied examples is the duality between N=4 super Yang-Mills theory with gauge group SUN on the gauge theory side, and on the gravity side is an ADS5 times S5 background of string theory, and both ADS5 and S5 have the same radius of curvature. The radius is denoted by L. And the correspondence between the parameters is that, it being a string theory on the right-hand side, there's two parameters. There's G string and the string length. And the correspondence of the parameters is the G Yang-Mills squared over 4 pi is G string. And then lambda, which is the TOF coupling, G Yang-Mills squared n is the radius of ADS to the 4th divided by the in string units, so divided by the string length to the 4th. And if one takes two limits, then the theory in the bulk can be approximated by a two-derivative supergravity theory, classical supergravity theory. In order to suppress the loop corrections in the bulk, one needs n much larger than 1. And in order to suppress higher derivative interactions in the bulk, one needs the TOF coupling to be much bigger than 1, G Yang-Mills squared n. So in this limit, if both limits are taken, then in the bulk, we have a 10-dimensional supergravity theory for which ADS5 times S5 is a solution to the classical equations of motion. So ADS5, I introduced it as that hyperboloid embedded in RD, 2. And I wrote down, just to remind you, the parameterization in terms of the coordinates T, X, and Z. Maybe I can also write down the metric in these coordinates. So the metric is L squared over Z squared times minus dt squared plus dx squared plus dz squared. So here X runs over the spatial coordinates, T is time, and Z is an extra coordinate. Okay. So that's ADS. N=4 super Yang-Mills is a gauge theory with gauge group SUN. It has N=4 supersymmetry, and that requires that in addition to the gauge field, we have other fields that are related to the gauge field by supersymmetry. And these other fields are fermions as well as 6 scalars. And in order to not confuse the notation, I reserve capital X for the embedding coordinates of ADS, and I'll call the scalar in N=4 super Yang-Mills phi. There's 6 scalars. So all of these transform in the adjoint of the SUN gauge group, and the action for N=4 super Yang-Mills is the usual, starts with the usual term for Yang-Mills action, 1 over 2 G Yang-Mills squared trace F mu nu F mu nu, and then there's all the other terms that are required by supersymmetry, in particular kinetic terms for the scalars, the fermions, as well as interactions. And so that's sort of the summary. And what I thought would be a good goal for this lecture and the next is to show you some tests of ADS-CFT that go beyond supergravity. And for that, we're going to need to learn some various techniques and various other results. So I thought it would be fun to do that. Are there any questions? Okay. So I wanted to start. So last time I discussed this Wilson loop that computes the quark-antiquark potential. I want to discuss a different, start by discussing a different Wilson loop now, namely a circular Wilson loop. So maybe I can just draw it here. So if we are in ADS-CFT, and so suppose this is ADS, suppose we have the Wilson loop, the contour of the Wilson loop is a circle of some radius. This is the contour. I realized last time I didn't actually write down the formula for the Wilson loop, so let me write it down now. So the Wilson loop operator is 1 over n trace e to the path order exponential. Well, that's why I didn't write it down. Integral ds I a mu x mu dot, and then so the usual Wilson loop just would stop there. So this is in Euclidean signature. In n equal 4 super AMLs, sometimes it's useful to consider a different kind of Wilson loop operator, where in addition to having the gauge field in the exponent, one also has one of the scalar fields. So I'm going to write it like this: zeta times phi I of x times theta I times the magnitude of x dot. And the integral is over the contour C. So the usual Wilson loop is the one with zeta equals 0. However, the Wilson loop with, there's another special value of zeta, which is zeta equals 1. Sorry, I didn't say what this theta is. So phi is a scalar, and theta is just a unit vector on the sphere. So theta I dot theta means theta I is equal to 1. The theta sum up to 1. Theta squared sums up to 1. And the reason why having such a term is useful is that this special value of zeta, namely at zeta equals 1, then this Wilson loop, for special choices of contour, this Wilson loop would be supersymmetric, in particular for the circle. And because of that, the expectation value of the Wilson loop can be computed exactly at all n and g angles. And I'll show you the formula for it. I guess one comment is that, so last time I was talking about the Wilson loop with zeta equals 0. The difference between zeta equals 0 and zeta equals 1 at strong coupling is only subleading in 1 over lambda. At weak coupling, of course, the two are very different. But at strong coupling, at leading order in large n and large lambda, they give the expectation values are the same, regardless of whether zeta equals 0 or zeta equals 1. The subleading terms differ. Good. Any questions about the definition of the operator? Good. So the at strong coupling, the rule for computing the expectation value of the Wilson loop is that this is e to the 1 over 2 pi minus 1 over 2 pi alpha prime times the area of the minimal surface that ends on the contour C. So we have to continue this in the bulk. Maybe I can draw it a little bigger so that we can see it. Unfortunately, my idea space is not that big here, even though it's infinite. So the contour, there's a string worldsheet that extends in the bulk, and we should supposed to compute the its area, extremize over it, and the expectation value would be given by this expression. Yes. Yeah.
That naturally selects some value of zeta over there, because from the bulk perspective, that's just one quantity that you are calculating.
So it doesn't matter which zeta, for which at leading order, it doesn't matter for which zeta we compute. Zeta is going to be relevant only for subleading terms. Another way of, if you ask, another way of, well, more information on this is this. So this Wilson loop with zeta equals 1 corresponds to the string sitting at a specific point in the S5 directions, namely the point that's described by this theta. With zeta equals 0, so that's the string obeys Dirichlet boundary conditions in the internal directions. If we set zeta equals 0, then there's a different choice of boundary conditions. It would be Neumann boundary conditions. Yes. Yeah.
We set the angles of the S5 to 0.
No, we didn't worry about them. We assumed, sorry, no, zeta was 0. We assumed that the string sits at the point on the S5. But one can make a different assumption where we have to integrate over the S5 coordinates. We have to integrate over the location of where the string sits on the S5. So if we assume it sits at the point, then zeta equals 1. If zeta equals 0, then we have to integrate over the where it sits on the S5. The rule is that so at leading order, that's not going to matter. When that's going to matter is when we consider fluctuations of the string worldsheet, and the boundary conditions that the string obeys will matter.
One can tune what zeta this minimal surface computes the Wilson loop of, is it?
Yes, that's right. One can also compute the one with arbitrary zeta by specific choice of boundary conditions. I didn't want to get into all those details, but so you can think about this as think about the Wilson loop with zeta equals 0, and then turning on zeta is like turning on an operator that's located on the Wilson loop. And then there's a flow of that coupling of zeta. I have to find the fixed points. The fixed points are zeta equals 0 and zeta equals 1, a strong coupling. Okay, good. So there's one trick for figuring out what this surface is. And the trick relies on conformal symmetry. The theory is conformal, so there's conformal symmetry. There exists a conformal transformation that takes the circle into a straight line. And for a straight line, we know what the string worldsheet is in the bulk. It's just a straight string worldsheet that extends all the way down. So there is a coordinate transformation in the bulk that takes this string worldsheet to the completely straight down one. So trick. I mean, of course, we could also just solve the Euler-Lagrange equations for that problem and get the same answer. So there's a string worldsheet that's just a straight line like this. And the conformal transformation, it takes that to the circle. And if we work through the details of the conformal of the coordinate transformation, this straight world sheet is going to become a half sphere of the radius, whatever radius the contour has on the boundary. If you, well, I guess I have another board here. So the coordinate transformation is this. So for the straight world sheet, we can use the coordinates t. Let's just set t equals 0. We have x1 is equal to x. Let's say x runs along the boundary direction. x2 equals 0, x3 equals 0, and z equals z. So we parameterize it with x and z. What this means is that the xi coordinates are given by 0, Lx over z, 0, 0, z over 2, minus 1, plus L squared minus x squared over z squared, and z over 2 times 1 plus L squared minus x squared over z squared. And then, as I said, is just a coordinate transformation. The coordinate transformation is little x is Lx1 divided by L plus x2. So the coordinate transformation is done in steps. This is the first step. And then z is L times square root of L squared minus x1 squared minus x2 squared divided by L plus x2. So I'm just rewriting the two coordinates parameterizing the straight world sheet, x and z. I'm rewriting them in terms of two new coordinates, x1 and x2. It might seem like a funny rewriting, but you can check in Mathematica that after this rewriting, those embedding coordinates for this straight world sheet become 0, Lx1 divided by square root of L squared minus x1 squared minus x2 squared, 0, 0, Lx2 divided by square root of L squared minus x1 squared minus x2 squared. And the last one is L squared divided by the same square root. I hope this is still readable, even though it's a little small. The idea is that I just did a coordinate transformation. And then we can do a conformal transformation on the boundary, which means an isometry in the bulk. Isometries in the bulk are just Lorentz transformations in this d plus 2 dimensional space. So in particular, we can do a rotation in the 2, 4 directions. So this is the second, this is the fourth. So 2, 4 rotation. And we can take this and put it in the second position, and the second to last position will have a 0. So that this would be 0, Lx1 divided by square root of L squared minus x1 squared minus x2 squared, Lx2 divided by the square root of L squared minus x1 squared minus x2 squared. And then we're going to have 2 zeros, and then L squared divided by the same square root. And one can then check that this specific parametrization, so it's a surface in ADS, this is exactly how we would parameterize a hemisphere of radius L. So this would be a hemisphere of some radius. Though what we got from this 2, 4 rotation is a hemisphere of radius L. So let me write that down somewhere. I can go. Room's too big, too many boards. We'll go over here. So this is what we got there, was a hemisphere of radius L. And then what we can do is do another conformal transformation, which is a rotation in the last two coordinates, in the 4 and 5 coordinates. And that corresponds to dilatation. And from a hemisphere of radius L, we can get a hemisphere of any radius we want. So in particular, we can get a hemisphere of some radius A. In ADS, all of these are just coordinate transformations. So I can just map by a coordinate change the straight world sheet to the hemisphere. Questions about this? Yeah. In this approximation, it doesn't. But yeah, it would backreact on it. It would backreact on the geometry. Yeah, one would have to consider that. Right. Good. So now let me compute the area of this string worldsheet that's either a hemisphere or a straight line. What do we expect to get if they're related by a coordinate transformation? Same area. So let's see if we get the same area. So let's just do it for the straight one first. So for the straight worldsheet, the induced metric on the worldsheet is L squared over Z squared times dZ squared plus dx squared. So then the action is 1 over 2 pi alpha prime times the area. The area is the integral of the square root of the metric. The square root of the metric is L squared over Z squared times dZ dx. I can integrate dx and I can get delta x, the spatial extent. What kind of integral is this? So it's from 0 to infinity. But from 0 to infinity, is it finite or is it infinite? Infinite, we discussed this last time. Diverges, we have to regularize it by putting some epsilon here. So what we get is that L squared delta x divided by 2 pi alpha prime times 1 over epsilon. Like last time, the 1 over epsilon term should be regularized away. So the expectation value of the straight Wilson loop is regularized 0. So the expectation value of the straight Wilson loop is 1. Good. Let's just do the same computation for the circle. Sorry? This is the field theory definition. In ADS-CFT, the way we compute it is by that formula that includes the 1 over. So for the circle, S, well, let's just figure out what the area element is. So if we have something like this, let's just parameterize it with a Z coordinate like that and figure out in this, for a small portion of it, of length dz in the Z direction, what is the area of that? So D area is, so first of all, there's the L squared over Z squared factor in front of the metric. So that we're going to have to include. And then it's the length of this circle, but there's more length here because this is tilted. So it's tilted by some angle. So if we call this angle theta, then this would be 2 pi times this distance rho over sine of that angle theta times dz. But rho over the sine of the angle is just the radius of the sphere, a. So this is just L squared over z squared times 2 pi a dz. This is the area element. To compute the actual area, we have to integrate the area element. And then we have to multiply it by 1 over 2 pi alpha prime to compute the action. So the action would be 1 over 2 pi alpha prime times the area element. So 2 pi a L squared are constants. I can put them up front. 2 pi a L squared. And then we have to do the same integral. dz over z squared. But this time, it's from where to where? It would be 0 to the maximum z, which is a. But of course, it's also, again, divergence. It would be from epsilon to a. And this integral is L squared over alpha prime times a over epsilon minus 1. Because of the upper limit of the integral, we get the 1 over a, and that 1 over a cancels the a up front. So the regularized action is minus, we forget about the 1 over epsilon term, so it's minus L squared over alpha prime, which according to the dictionary, alpha prime is L string squared, so this would be minus square root of lambda. So this means that the expectation value of the circular Wilson loop is what? E to the plus square root of lambda. So surprise, even though the two calculations are related by a coordinate transformation, the answers are different. Why are they different? Yeah.
The answer. So a conformal transformation gives the angles, but not the area, right?
No, conformal transformation is nice. In the bulk is an isometry, so it should preserve the area. It preserves the area element.
After when you transform operators, it's like easy, easy prime.
No. The answer is they're different because they're infinite. They require regularization. The regularization actually breaks the transformation. So they're different. Now, in the field theory, we have to interpret this somehow. Why are they different? Why is a circle not the same as a line, even though they're related by a conformal transformation? Yeah.
-1 is also a counter term, right? Why can't we not just throw it away as well?
The only divergence that we have is proportional to the perimeter. This is not proportional to the perimeter. The only counter term that we can add is something proportional to perimeter. So in the field theory, just from a field theory perspective, why is a circle not the same as a line, not exactly the same as a line after a conformal transformation? What do we have to do? So take the line, add a point at infinity, and then conformally transform, and then you get the full circle. The full circle minus the point is the line. So the full answer must, in some sense, come from the point at infinity. So just from one point. So that led Drucker and Gross. You could do the exact same thing at weak coupling. So that led them to conjecture that the answer for the circle comes from one point. So it's a field theory supported at one point. Field theory supported at one point is just a regular integral. You just integrate over the fields at that point. So the answer should be a matrix model. And they figured out what the matrix model is. They conjectured it, and then it was later proven. So the matrix model is this. You start with a partition function. It's just a Gaussian matrix model. So integrate over matrices M. So M would be Hermitian and traceless if the gauge group is SUN. E to the minus 8 pi squared over G Yang squared times trace of M squared. That's the matrix model. And the Wilson loop insertion, or the Wilson loop expectation value, is 1 over Z times the same integral, but with an extra insertion that corresponds to the Wilson loop. So it's 8 pi squared over G Yang squared, trace M squared in the exponent. And for the Wilson loop, we just have 1 over N times the trace of E to the 2 pi M.
The rank of the matrix.
And yeah, sorry, and by. Well, it's Hermitian traceless, n by n Hermitian traceless. That would correspond to SUN. If we don't impose a tracelessness condition, then it would be UN. You can. It's obvious how to generalize it to even to other representations for the Wilson line, other gauge groups. So, well, they conjecture this, as I mentioned. This was later proven using supersymmetric localization. But well, how do we see that this makes sense? Well, these are just Gaussian integrals over there, which can be done. So Gaussian integrals. And the answer is known for all G angles and all N. I can write it down. I'm not going to prove it. It's 1 over N times the Laguerre polynomial n minus 1 of minus G angles squared over 4. And for SUN, it's e to the G angles squared over 8 times 1 minus 1 over N. This is the exact answer, all G angles, all N. One can check it at weak coupling, that it works. One can check it at strong coupling. How do we check it at strong coupling? So at strong coupling, we should get that the expectation value is approximately e to the square root of lambda. How do we get that? Well, one can approximate this formula. No, this is the full answer. This is the full answer. All N, all G angles. Yeah, that's why supersymmetry is so powerful. It allows you to compute some quantities. Even in a strongly coupled theory, in like, moderate coupling, you don't have to take any limits. You can figure out some answers at all G angles, all N. So at large N, fixed lambda, and I'll show you next time how to get this answer actually without doing that. One can get this expression approximates to 2I1 of square root of lambda divided by square root of lambda plus order 1 over n squared corrections, where I2 is a Bessel function. So now this answer is at leading order in large N, but all orders in lambda. And then one can open Wikipedia, find the asymptotics of the I1 Bessel function. And this will be square root of 2 over pi times e to the square root of lambda times lambda to the 3/4 plus subleading corrections. So it's this square root of lambda that one can then reproduce from this matrix model. Drake and Groves conjectured it based on weak coupling computations, and then they checked it against strong coupling. But as I said, it was, so the matrix model That's related to the fluctuations, yes, of the strain. So in particular, if we consider the Wilson line with the zeta equals 0, that would have a different factor of the different power of lambda. It wouldn't be lambda to the 3/4, different power of lambda related to the fluctuations. So the matrix model is proven and generalized by Princeton using supersymmetric localization.
Take this matrix model because this is not some.
The matrix model does not have any supersymmetry.
It's not some super matrix or.
No, it's a regular Hermitian traceless n by n matrices.
Okay.
Yeah. So for example, if we considered UN, not SUN, and we didn't have the tracelessness condition, and we took n equal 1, that's just an integral in one variable. So that you can probably do in your head what the expectation value of the Wilson line is, the circular Wilson line in U1 theory. It's just a one-dimensional integral, Gaussian integral. Okay, so what this gives, this is a test. So this is a test of ADS-CFT. And what I'd like to show you is some more impressive tests that go even beyond the leading order. That involve correlation functions of local operators. Yes.
Say that is that with this
yeah, that's a result that comes from that matrix model. One can evaluate that matrix model, and it gives that Laguerre polynomial, the matrix integral.
Is that done with supersymmetry?
No. This is, well, it's a Gaussian integral, but it's a Gaussian integral in n² - 1 variables. So it's not actually that trivial. But there's a huge technology for how to compute these matrix integrals.
So where does supersymmetry play?
Supersymmetry plays a role in deriving that the fact that the expectation value of the Wilson loop is given by that integral. That's where supersymmetry comes in. Yes. It's half BPS. It has more supersymmetry than that. Yeah. Yes, this is what Princeton did. Yeah, and this was his goal. His goal was to prove that formula, that matrix model. Okay, good. So I wanted to discuss a little bit some analogous checks, but more impressive in the sense that they go beyond the supergravity approximation for correlation functions of local operators. So first, that's probably going to be, the actual computations are going to be next time. Today, I just wanted to set up the problem and figure out an expectation for what we should prove. Okay, so let me review extremely briefly how to compute correlation functions of local operators in ADS-CFT. So for that, we need two concepts. The first one is conformal primary operators. So what are those? So a CFT is invariant under the conformal algebra. The conformal algebra is SOD, 2. And the generators consist of the Lorentz generators M mu, translations P mu that act as derivatives, special conformal generators K mu, and dilatation B. And what's a conformal primary? A conformal primary operator, O, is a primary, the conformal primary, provided that when we put it at the origin, it's annihilated by K. So all the operators in the CFT, transforming representations of SOD comma 2, and this is a way to build the representations. First, figure out which operator, when placed at the origin, is annihilated by K. There's a primary, and all the other operators are derivatives, are obtained from that operator. All the other operators in the same multiplet are obtained from this operator by acting with a momentum generator, which means taking derivatives. So derivatives of O are called descendants, conformal descendants. Good. That's the first concept that's needed. The second concept that's needed is the notion, related to the fact that we're in a gauge theory with a parameter n, and we're taking n to be large. So the concept is single trace operators. So at large n, the operators can be broken down into single trace, double trace, triple trace, and so on. Double trace and higher would be multi-trace. So what do they look like? Well, for example, single trace examples of single trace operators would be, for example, trace f mu nu, f mu nu. I think the name is self-explanatory. We're just taking only one trace over the color indices. That's what single trace means. Another example would be trace phi I, phi j, minus 1,6 delta ij, phi k, phi k. This operator is going to be important later. And so on. As an example of double trace, we can have, for example, a trace f mu nu times trace f rho sigma, and so on. So we're taking two traces. Triple trace, take three traces, and so on. So with these two concepts, I can say how ADS-CFT works for local operators. So ADS-CFT, it's the single trace primary operators that should be identified with fields in the bulk. So this would be correspond to single particle states created by a bulk field, by the bulk field phi of z and x. So we can think about, if we have a weakly coupled theory in the bulk with some fields, we can quantize it, expand the fields in mode. We have creation annihilation operators. If we act with one creation operators in just one, that would be a single particle state. If we act with two creation operators, it would be two particle state, and so on. Single particle states correspond to single trace operators. Okay, so to each single trace conformal primary O, there exists a field phi in the bulk. And of course, in order to match whatever properties O might have in the field theory, the field in the bulk phi must obey some analogous properties. I'm not going to go through the full list of properties, but one can make a list of properties. I'll go through only one of them, namely the mass of this field. Okay. So what is the precise relation between the operators as far as correlation functions go? What is the precise relation? We start with a bulk field and take it to the boundary of ADS to get the boundary operator O. So naively, it should be simple. However, the limit is a little subtle, and I'll discuss what the subtlety is. To discuss what the subtlety is, I have to introduce one more notion, which is that of the conformal dimension. So suppose O of x is some operator, scalar for simplicity, with scaling dimension delta. What that means, scaling dimension delta means that under the scale transformation, x goes to lambda x, the operator O transforms into lambda to the delta times O of lambda x. This property, for example, implies that the two-point function of an operator O of dimension delta goes like 1 over x to the power 2 delta. Another way of saying this is that when we place the operator at the origin, so O of 0 is an eigenstate of the dilatation operator with eigenvalue delta. So where the dilatation operator is x mu d by dx mu. Okay. Yes. Sorry.
The scaling is plus or minus, right?
Here. Plus. Oh, I got the signs right. Well, if it's not plus, then what I'm going to say is not going to work. So it better be plus. Okay, so well, it depends on what the arrow means. The idea is that if we make this transformation, then correlation functions will be invariant. Yes. Sorry?
From the boundary operator to the bulk operator, so there are systematic.
Oh, that's a very hard question. How to go from the boundary operator to the bulk operator. The other way is easy. So I'm going to tell you the other way. Okay. So the other way is that O of x. So if phi is the dual of O, so phi of z and x is dual of O, then O of x up to some normalization is the limit when z goes to 0 of 1 over z to the delta times phi of z and x. So let me give a brief justification of this, just to see that it makes sense. So in ADS, of course, on the boundary in a CFT, dilatation is not an isometry. It doesn't preserve the metric. It just changes the metric by a scalar factor. But in ADS, dilatation, which is x goes to lambda x, accompanied by z goes to lambda z, is an isometry. So that means that if we go from x to lambda x and from z to lambda z, the field phi should stay unchanged. Or the field phi should go to the field at that other position. So that means that phi of z and x goes to phi of lambda z, lambda x, because it's an isometry. So then let me check that that equation actually makes sense. So if I have O of x defined by that equation, under the change, x goes to lambda x, z goes to lambda z, this becomes the limit when z goes to 0, and O divided by z to the delta times phi at the changed location, which is lambda z, lambda x. And then we can do, it's a limit, so z is a dummy variable. We can change from z to z over lambda. So then this becomes the limit when the new z goes to 0, and O, but then this z becomes z over lambda, so lambda is in the numerator, lambda to the delta over z to the delta times O of z and lambda x. And that is precisely the definition of lambda to the delta O z lambda x. So this matches. Let's see if. Sorry? Oh, I'm sorry. No z. Yeah, I should read my notes more carefully. Sorry? Oh, 5. Yeah. I should really read my notes. Okay, good. Yes.
They correspond to something like phi square, or is it?
Double trace operators would correspond to two particle states of phi. So it's as if we consider two different operators. So a double trace is a product of two traces. It's as if we consider those two single trace operators and we take them to the same point.
Like phi square or not?
It could be generated by phi squared, I guess.
Or is it more delicate because it's
yeah, I think that would work. I think that would work. Okay. So good. And as I mentioned, there's a, for each property of the operator O, there's a property of the field phi. And in particular, the fact that O has scaling dimension delta implies a property for phi. So note, just requiring that we take a finite limit. So when we take z to 0, the fact that we get a finite answer, that implies, it's a simple calculation, but I probably won't do it because I want to get to other things. It implies that the mass of the field phi is m squared is delta times delta minus d divided by L squared. That's the full formula. So it's not going to be crucial for what I'm going to say. So maybe I'll just skip that proof. The proof involves just looking at the solution to the classical equations of motion. Unless people want me to do it. Yes, no, maybe. Let me try to see if I'll have time to do what I actually want to do. Maybe I'll get to it at the end if I have time. How about that? Good. So good. So now one can just use this limit. So the equation of the top of the board, the relation between phi and O, to compute correlation functions of O. So what one has to do is to compute the correlation function of the phi's in the ball, and then take some number of the phi's, however, depending on what the correlation function we want to compute on the boundary is, take those phi's to the boundary, and that's the correlation, and divide by 1 over z to the delta for each of them, and that's the correlation function on the boundary. Sorry, there was a question. Yeah.
So how is the picture modified when we have a descendant operator?
To have descendants, you just have derivatives. The descendant is just a derivative of a primary. So what you have to do is to compute whatever you compute for the primary, and then you take the appropriate number of derivatives, and you get the answer for the descendant. So correlation functions. I think the most interesting case of a correlation function where we'd learn something non-trivial would be a 4-point function. So focus on 4-point functions. And that's because in the CFT, the 2 and 3-point functions, any given 2 and 3-point function contains only a limited amount of information. A 4-point function contains much more information. So in a CFT, for example, the 2-point functions of 2 operators, OI of x, OJ of y, can be taken to be, we're just choosing the basis of operators, delta ij x minus y to the 2 delta. The 3-point function is also pretty simple. So OI of x, OJ of y, OZ of k. That's some coefficient Fijk divided by various powers of differences of x, y, and z. So it'd be x minus y to the power delta I plus delta j minus delta k. And then that would be x minus z to a similar power, and it would be y minus z to a similar power. The first much more non-trivial case is that of a 4-point function, where we have O of x1. So suppose it's the same operator, O of x2, O of x3, O of x4. This is 1 over x1, 2 to the 2 delta, x3, 4 to the 2 delta. So xij here would be xi minus xj. Times some function f of 2 variables u and v, where u is x1, 2 squared, x3, 4 squared over x1, 3 squared, x2, 4 squared, and v is x1, 4 squared, x2, 3 squared over x1, 3 squared, x2, 4 squared. And the function can be any function that's allowed by conformal symmetry allows any function of u and v. So that's why the 4-point functions are much more non-trivial than the 2 and 3-point functions. And for that reason, We'll just focus on 4-point functions. Okay. So how do we compute these 4-point functions? In the bulk, in principle, so as I said, we just draw the diagrams in ADS, and then we take the limit when, for a 4-point function, 4 of the points. So compute a 4-point diagram in the bulk, and then take the limit where 4 of the points go to the boundary. So in ADS, take points to the boundary according to that equation over there. So for example, if we want to do a 4-point function between some operators, we could consider diagrams where there's an interaction point in the bulk. So we can compute this when these points are arbitrary points in the bulk. So this would be just a product of propagators in the bulk. And then take the limit of those propagators integrated over the bulk point, and then take the limit where those propagators just go to the boundary and divide by 1 over z to the delta for each one. So this would be the 4-point function. For that, we would need to know the bulk propagator, but this is known. Bulk propagator. It's known, but the formulas are pretty complicated. So these are not easy computations. So for example, a propagator for a bulk field that corresponds to boundary operator of dimension delta, if the bulk field is a scalar field, between 2 points in the bulk. So it depends on some z1, x1, and some z2, x2. And it's some complicated function. So there's some normalization factor. And then there's a function, there's like 2 over some u to the power delta. Then there's a hypergeometric function, delta minus d plus a half, 2 delta minus d plus 1, and then minus 2 over u, where u is z1 minus z2 squared plus x1 minus x2 squared over 2z1, z2. It has a simple limit, simpler limit when one of the points here goes to, or both points go to the boundary. Then this becomes just a pure power of u. Okay, is at least in principle the procedure for computing correlation function clear? So we start with some theory in the bulk. We write down our propagators. We just expand it in powers of the fields. From the quadratic term, we figure out what the propagators are. The propagators solve the equation of motion in the bulk, whatever that equation is. For example, for a scalar field, it would be the solution would be something like this. And then we just use the usual quantum field theory rules where we compute correlation functions and then just take points to the boundary. Yeah.
Because I get lost with these things always. So you would have 4 of these green functions, one for each line there, and then you would have an insertion at the boundary and another one in the bulk, and you would integrate over all possible points.
Integral over a bulk point. So let me write down the bulk point as x. So let me combine this z and x. So z and x. Let me call that x. Okay. So then I have an integral over x, and I have, for example, for this diagram, is g delta x1, x, g delta x2x, g delta x3x, g delta x4x. And then afterwards, we just take the limit. Z1 goes to 0, Z2 goes to 0, and so on up to Z4. And we include 1 over Z1 to the delta, Z2 to the delta, Z3 to the delta, Z4 to the delta. I claim that gives the correlation function.
finite by default.
This expression will be fine. For contact diagrams, it will be fine.
And then the last question is, so this seems a quantum process in the bulk. You're doing Feynman equation.
Sure.
But okay, you told us that we do classical gravity in the bulk.
Yeah, it's not. Well, we could think about it in terms of that, but it could also be thought of as when we insert these operators on the boundary, we just turn on some sources for the fields phi that gets sourced into the boundary, and we're just really solving the classical equations in motion. And this is the first to first order. This is the integral that one would have to do in order to solve the classical equations in motion. Find the action with those sources on the solution to the classical equations in motion. Yes.
Diagram in the bulk correspond to some quartic vertex. Wouldn't that be more suppressed compared to, for example, some bulk free field with only graviton exchange?
No, it would be of the same order as that diagram that you have in mind. It would be suppressed compared to the diagram, to this diagram. But if there's some exchange here, that would be of the same order as that. I'm going to go over precisely the powers of n and the powers of lambda that appear in these calculations right now. That's actually what I want to do in the last however many minutes I have. So just want to go over the powers, and on Thursday we'll derive the powers from a field theory calculation and an example. Good. So for that, so we have to figure out the scaling in n and lambda. So we have to write down what the action is. So consider the action is this. So 1/16 pi g in 10 dimensions. And we have d10x squared to g. So at leading order, we have in 10 dimensions Einstein gravity plus whatever other interactions are needed by supersymmetry. But then, as I said, so that's to leading order. This is just a supergravity action. As I said, there are corrections to this. The corrections would be higher derivative corrections. So the first correction, even though it's not known in full generality, it would be, so the Einstein action has 2 derivatives. The next correction in string theory in 10 dimensions has 8 derivatives. So it starts with a specific contraction of 4 Riemann tensors, and then it's whatever else is needed for it to be supersymmetric. Because it has 6 more derivatives than that, it has to come with a power of the string length to the 6th power. The next term after that, that contributes to the scattering of to a 4-point function, would be 4 derivatives and 4 Riemann tensors that I'm going to write schematically like this. I mean, imagine there's many indices. They have to be contracted somehow. There's many ways to contract them. There's just specific linear combination. And whatever else is required by supersymmetry. And because this has 10 derivatives more than the Einstein-Hilbert term, this comes with string length to the 10th power. The next one is 6 derivatives on Riemann to the 4th, and 8 derivatives on Riemann to the 4th, 10 derivatives on Riemann to the 4th, and so on. So this is what this looks like. What we're supposed to do is to take this, expand around AdS5 times S5 of radius L. So then let's just try to figure out how things scale, how propagators scale, and how interaction vertices scale. So what we need to recall is that 1/G10, the Newton constant, that's proportional to 1 the string length to the 8 times G string squared. And in field theory quantities, there just gives n squared. So this is proportional to n squared. And another thing, because the string length appears here, another thing we have to remember is that L over the string length is proportional to lambda to the power 1/4. And that's all we need to know. So then I'm going to write down how the various things scale. So then the propagators, because we essentially have a 1 over n squared in front of the action, the propagators will scale like n squared. The interaction vertices that come from supergravity, so from the Einstein-Hilbert term or whatever else is related to it by supersymmetry, those would scale, the coefficient is also the same, 1 over G10. So they scale, oh, I'm sorry. Because we have n squared in the action, the propagators scale like the inverse of that, 1 over n squared. And the interaction vertices, because we have n squared in the action, they scale like n squared. Now, if we have interaction vertices from, let's come from r to the 4th, Riemann to the 4th from here, well, they scale like we have an n squared here and also string length to the 6th. So it'd be n squared times string length to the 6th. The string length to the 6th will be down by lambda to the 6 over 4. Lambda to the 6 over 4 is lambda to the 3/2. So those will scale like n squared over lambda to the 3/2. Now, interaction vertices from d to the 4r to the 4, for example, would scale like n squared divided by, well, 1 over lambda string to the, they scale like L string to the 10th, which goes like 1 over lambda to the 10 over 4, which is 5/2. And so on. So to actually compute, one needs the normalization of the boundary operators and the convenient normalization. So normalize O of x, the boundary operators, such that their 2-point function scales like n squared. That's a convenient normalization for figuring out this counting, and one can do any other normalization. And then what happens is that whenever we have one of those propagators that goes to the boundary, we have to multiply them by an extra n squared. So this means that for boundary anchored legs or propagators, we have n squared times 1 over n squared, so we have n to the 0. So for those, we don't have to include anything. So with that, we're ready to figure out how various diagrams scale. So maybe I can do a few. So if we think about the 4-point function of O, whatever O is, at leading order, so here I'm going to write down, it's easier to write down, instead of writing down the boundary as flat, I'm going to write it as a circle, but imagine that this circle is actually a plane. And the operators I'm going to put on the boundary, which is the boundaries of the circle. So leading order would be something like this, 2 propagators like that. So this would go like, a propagator is well, this would be like the 2-point function squared. So this would be like n to the 4th. For this one, we cannot use the sorry, we can use the counting. It's 1 over n squared for each propagator, but then I have 4 n squares for the vertices, and I get n to the 4th. The next contribution is when we have a contact interaction. So the boundary anchored propagators, if they have only one leg on the boundary, they don't contribute anything. The only thing that contributes is the vertex in the bulk, and the vertex in the bulk is like n squared. So this would scale like n squared if the vertex comes from the Einstein-Hilbert term. And then we can figure out how other things scale. A exchange diagram was mentioned. So we can do the scaling of that too. So for the exchange diagrams, it will look like that. Again, if the vertices come from the Einstein-Hilbert action, then each vertex scales like n squared, but there's one propagator in the middle that scales like 1 over n squared. So overall, this would also scale like n squared. The next more complicated thing we can have is a bulk interaction that comes from this Riemann to the 4th interaction vertex from a higher derivative vertex from here. So the interaction, those interaction vertices scale like n squared over lambda to the 3/2. And again, we have propagators that are anchored on the boundary, so they don't scale with n. So this would be n squared over lambda to the 3/2. I probably have to end, right? A couple minutes. Okay. Let me do let me do a couple more diagrams and then I'll stop. So okay, so hopefully this is clear. So if I have, then the next one would be d to the 4 to the 4. This will go like n squared over lambda to the 5/2. And let me do a loop one just to see what the difference is. So we can have, so tree level diagrams, we can have an infinite number, and then we can have loop diagrams that look like, the first one looks like this, where two vertices, both vertices come from the Einstein-Hilbert action. So each vertex would scale like n squared, and we have two propagators that scale like 1 over n squared. So it's 2n squares, and then 2 1 over n squared, so we get n to the 0. We can also have loop diagrams that come with one vertex from supergravity, one vertex from the Riemann to the 4 term, and then this would scale like n squared. This would scale like n squared over lambda to the 3/2. And the two propagators would scale like 1 over n squared. So this would be n to the 0 over lambda to the 3/2, and so on. So loops scale, tree level diagrams scale like n squared. Loops scale like n to, one loop diagram scale like n to the 0. And then there's various powers of lambda depending on what the vertices are. Two loops scale like 1 over n squared with various powers of lambda depending on what the vertices are. Three loops is 1 over n to the 4th, and so on. So next time we'll see the structure from a field theory computation. So I guess yeah, see you Thursday.
Thank you for the very interesting lecture. Any further questions?
That's about this matrix model. So the argument that trivial loop is given by matrix model, that's relies on SUSY. But on the other hand, you have this argument that relation between straight line and circle line is given by matrix model because you have one point.
That was their argument, yes.
Right. So is that matrix model, does it depend on whether one considers supersymmetric line or non-supersymmetric? Is it even true always? Dependent of supersymmetry transition.
I think for the I think there's something tricky about the non-supersymmetric one because that one requires some regularization. So maybe there's some subtleties related to that. The SUSY one, the SUSY-Wilson loop with computed perturbation theory is finite. So it's simpler to argue this thing in that case. Yeah, I don't really know the answer to your question. I mean, I find it very interesting. That one can make this argument.
Expect that straight line also not just one, so there are corrections on, but that argument suggests the transition is still beyond the.
Yeah, that's right. And one can generalize this to other situations. For example, you know, if you consider 3D CFTs in flat space, the free energy is 0 after regularization. On the sphere, we have this F coefficient is the sphere free energy. One can make the exact same argument. It's the difference between a plane and a sphere is 1 point. So the sphere free energy should be described by a matrix model. And indeed, that's true in supersymmetric theories, but we don't know if it's true or not in non-supersymmetric theories. It would be very interesting to understand this. What Drucker and Gross say is that this relation between, this difference between line and circle is some sort of anomaly, some sort of anomaly under inversion. But I don't think that has been made precise. It would be interesting to study it in that language if possible.
Sorry, can you explain again the mismatch between the circle and the line from the gravity point of view? Because I understood that we assigned it to source computation 3 infinite, and it's a different regularization. But if the regularization is responsible, maybe I can find a funny way to regularize the circle computation in order to get actually 0 again. But
yes,
that
is not the case. Yeah, the way to regularize is, well, if we want to get the field theory answer, there's a way to regularize it. You just cut it off as some finite z.
Oh, so there is a field theory induced way of regularizing it.
Well, yeah, because this would correspond in the field theory, this would correspond to adding a perimeter term.
Okay.
Right? If we do something else in the bulk, then we wouldn't be adding a perimeter term.
I'm not actually entirely free to regularize the gravity computation as I want. If I match my results, if I want to match my results with quantum theory.
That's correct. There are some constraints on the way to regularize. Yeah.
Indeed, giving you correction with n. So
in n and in 1 over lambda, in 1 over n and 1 over lambda. Yeah.
So, I mean, are they really related to string? You know, like the perturbative expansion in string?
Yes, you can think of these diagrams whenever you have a bulk line. You can think of thickening it a little bit, and it's a closed string that propagates. You can also draw a string diagram. However, you wouldn't be able to compute that string diagram in ADS. You can compute it in, in flat space, but not in ADS. So yeah, each of these fields that were kept correspond to the lowest modes of the lowest oscillation modes of the strings, the string theory strings. So they all correspond to like some small string propagating.
All right, any further questions? Yes.
How do people usually think about going from a boundary operator to the bulk? How do people think about going from a boundary operator to the bulk?
From the boundary operator to the bulk field, that's called bulk reconstruction. And that's very subtle. I think the story is not completely figured out. I think if one knew precisely how to do that, then that would go a long way towards proving ADS-CFT.
All right. Any questions?
Yeah, sorry, maybe I can say one more thing. I mean, there's, in the bulk, the metric in a quantum theory, the metric is fluctuating. So even defining the question precisely is interesting.
Right. Let's thank Silvia again.